Here's the last of our matching questions, number 15. It's polynomial, and it has zeros at -3, -2, -1/2, and +1/2. And the multiplicities for each of them are 1, 1, 1, and 1. The y-intercept is this number here at the end, -3/2, because if we substituted 0 for all these x's, those terms would all vanish. So the y-intercept is at y equals -3/2. The degree of the leading term is 4, so it's even. And there's no sign in front, so it's positive. That leading coefficient is positive. So now we look for a graph, the graph of a polynomial with zeros at -3, -2, and plus or minus 1/2. And we see that graph C is the only graph that has zeros in those places. B and E have different zeros. Also, the multiplicities of their zeros are not all 1. So graph C and graph F have 4 zeros, each with multiplicity of 1 because the graph slices through at each of those locations. The y-intercept is -3/2 or -1.5 for both. So what distinguishes is the fact that 3 of the zeros for this graph are negative, and 3 of the zeros for this graph are positive. And we'll go back and take one more look and see that 3 of the zeros for this function are negative, and so that means that C is the matching graph for that function. Next, we'll move on to the exponential and logarithmic equations. We're supposed to solve. Solve means find an x value that will make the equation true. For number 16, we have an exponential equation, and we want, our first goal is to write both sides with the same base. Can 8 be raised, or can 2 be raised to some power to give us 8? Yes, it can. 8 is 2 cubed. And so inside some parentheses, that's very important, inside some parentheses, we place 2 cubed, which is equivalent to 8. Then we use the power property to bring that 3 outside those parentheses, but when we do, we have to remember that this x plus 4, that entire expression, belongs in parentheses, because we will then distribute the 3 through these parentheses, giving us 3x plus 12. Now both sides have the same base, and we can eliminate those bases and set the exponents equal to one another. 5x equals 3x plus 12. I subtract 3x from both sides to get all the x terms on one side, giving me 2x equals 12, and then I multiply both sides by 1/2 or divide by 2. It's the same thing, to give me x equals 6. Excuse me. In number 7, we have 2 logarithms on the left side and a number on the right, and we're going to use the product rule to write these 2 logarithms as a single logarithm. So the base is the same, so we have log base 4, and then we'll multiply the x times the x plus 6. It's very important to remember to put those multiple terms inside parentheses, and we then distribute that x to simplify. So we multiply the x times x, x squared, and the x times 6, 6x. And so now we have the logarithm base 4 of x squared plus 6, the entire expression x squared plus 6 equals 2. The easiest way to solve this now is to write the equation in exponential form. We remember that 4 is a base, and we place 2 as its exponent and bring this expression inside the logarithm here to the right side of the equation. 4 squared is 16, and so what we now have is a quadratic equation. If we subtract 16 from both sides, then we have the entire quadratic equation equal to 0. To solve this, you can use the quadratic formula if you want, if you're weak in factoring, but just be careful because there's places where you can trip up using the quadratic, just like there are when you factor. But this is easily factorable, and the two factors are x plus 8 and x minus 2, since 8 times negative 2 is negative 16, but 8 plus negative 2 is positive 6. We set each factor, x plus 8 and x minus 2, equal to 0 and solve, and our possible solutions then are x equals negative 8 and x equals 2. But we cannot take the logarithm of a negative number, so x equals negative 8 is not a viable solution. It's what we call extraneous, and so x equals 2 is the only legitimate and defined solution for this equation.